extra heart to learn something new. So learning something new is a different thing because that only can nourish your learning and your talents. So today, my name is Nivya. I am the host for this event. This is a very momentous journey for Nest Digital because we are successfully launching the second hackathon on the topic Data Lakehouse. And we have different speakers from top MNCs are here. And today, I can say that as you all know that like 80 to 90% of organizational data is a very phenomenon, is having a phenomenon value. Because these data is having sometimes from the client mails till the production deadline videos. So these data are very complex to store as well. So storing a data is a complex one. So what is the solution? So this which leads to a creation of an architectural platform called Data Lake. So I'm not giving you a more explanatory views on the Data Lake because we have some eminent experts from different industries. So next, I'm moving to the core segment or core duty of today's event. It's my pleasure and I would like to welcome our beloved Executive Director and CEO, Nazneen Jahangir, to this event. Then, thank you. Then I would like to invite our Chief Technology Advisor, Mr. Nitin Malliya, and his Technical Excellence team, Mr. Manu Mukundan, and Mr. Sajikumar VK, the Technical Architects of Nest Digital, and their team to this event. Yes, there is a person needed for coordinating an event, for supporting all the hackathons or all the training activities of Nest Digital. Yes, we have one person, our Vice President, Nest Digital Academy, Dr. Pradeep S., to this event. In addition, I cordially welcome the Placement Division Head, Dr. Biju Paul, to this event because he is the person who he coordinates all activity and share this venue for conducting this hackathon event. So I cordially welcome him to this particular event. Finally, yet importantly, I would like to thank Rajagiri School of Engineering and Technology for being a part of this milestone event with Nest Digital. Thank you. Now, I request our beloved Executive Director, Nazneen Jahangir, to give our facilitation note.
afternoon, everyone. Dignitaries often on dais, fellow Nestians, and the participants of the hackathon today. It gives me great pleasure to stand here today, specifically because this is the second series of hackathon Nest Digital is part of, and it has always been in emerging technologies. It is the core objective of the group and Nest Digital specifically to work with emerging technologies and provide solutions to our world-class customers. So we are very proud today to make sure that we are part of the second series is successfully to be run out today. The first one was in microservice, and we had tremendous participation and feedback for that session. So I'm sure that the participants today go back with great feedback and great takeaways, specifically because we've got eminent leaders in Data Lakehouse to talk about it and educate and enlighten each one of you today. So if I take a moment, I see this whole thing as we are in an era where we are going into chat GPTs, where from chatbots, we are moving into natural language processing chatbots. So they understand human languages, natural processing languages. So when we stand in such a position, the data is the new oil. So unless we are able to process and analyze this data and create meaningful analytic out of it, it does not make sense. It is just something, it is just a huge dump of data. So when we say oil, all of you are aware that oil on its own does not give us anything. You're processing it, analyzing it, and refining it for all the productivity activities that we get from it. So data warehouse, like Nivya was saying, I'm not the expert. We have got the experts here to talk about it. But on one line, if you ask me, it is a new architectural design which will allow you to process the data that is available, and it's a data analytic solution that I would say it is. So today I take a moment to thank Rajagiri for allowing to use this facility and being a part of our journey. We are very glad to bring eminent leaders from MNCs here. So they are able to educate and enlighten you, people here as well as who are part of our live link here today. And I'm sure that you'll be going back with great takeaways. So all the best, guys, people who are part of it. And let's have a day of learning, and I'm sure it'll leave you nourished. Have a good day.
Thank you so much, ma'am. So today's agenda, I can see that the first session will be having the tech talk by the experts from MNCs. Then after lunch, we will have the hackathon. So when I'm going to the tech talk, the first speaker, her name is Ms. Madhavi Vakre. Sorry. First topic is about data lake, conclave, and the hackathon. So as a presenter, I would like to welcome Mr. Satish Titpur, C, the principal SW architect of GE. So Sir, I would like to glad to welcome to this program, and the topic which we are going to discuss is a data lake, conclave, and hackathon. So Satish, actually I would like to give few notes about yourself, because he's having 27 years of experience in GE, and he's working as a principal software architect at GE Healthcare India, and also working for the many different clients in healthcare domain. So thank you, sir, for coming over here, and please have. Sorry.
No, it's fine. Yeah, it has only the seat type. Good morning, everyone. Are you able to hear me? Okay. So, I was supposed to go as the third speaker, but I'm going as the first one. I had wished that the AWS and Microsoft would have covered the basics of health data lakehouse, and I was supposed to cover the lakehouse for healthcare. But since I am going first here, I'll try to cover a little bit of the basics of data lakehouse. Was any? Okay, I'm fine. So I'm going to cover a little bit of basics of what a lakehouse is or data lakehouse is, and then move on to the lakehouse for healthcare. And I hope our fellow speakers from AWS and Microsoft will go deep on the technology aspects of the lakehouse. Right. So here is what my agenda looks like. So I start with what is a lakehouse, why a lakehouse for healthcare. Then I talk about OMOP, CDM as the silver data model. I think that part will become clear, as I go through this presentation. Then I talk about acute care health lakehouse, which we do as part of our business at GE Healthcare, and then followed by learnings and references. Right. So what is a lakehouse? Right. So you would have heard about data warehouses, and you would have also heard about data lakes. I am assuming so. Very briefly, data warehouses was a concept developed in the 80s, where the data was brought to a central location, and they used star schemas, and they kind of produced analytics, business intelligence, and reports out of that. And with this concept of trying to derive more value out of data, as Nasli Jahangir was saying, it's like you extract value out of crude oil. Similarly here, to extract the value out of data, we need to bring in more data, and data warehouse was not geared for that. And that where people said, let me build a data lake where we can dump all the data, and then we think about how to extract value out of it, right? So that's where the birth of data lakes, roughly like 10-12 years back, where people build really huge storages and start dumping the data to it. And then they said, let me decide, what to do with that later, right? So this one, in data warehouse, it was not supporting all types of data. It didn't support image data, text data, and all those things. With data lakes, you have all the data, you have text, image, everything dumped. But if you want to derive value out of it, you needed to build, the data pipelines, processing that for every kind of use case, right? Including, if you want to do data science, learning, or even report, you need to build that. And everything was manual. There was no constructs available like in a relational database to do those things. So that was very time consuming and very, very manual effort and very expensive, right? And that's where the people thought about how about combining these two things, the best of both the worlds, and that was the birth of Data Lakehouse, right? So how do we kind of on that raw data thing, how do we build like technologies that can help that can bring some of the the best capabilities of like the relational database onto that, and that's how we got to this the Lakehouse architecture, right? So if you look at at the bottom of that we have structured, semi-structured, and unstructured data, and here in this stuff I'm kind of showing, my cursor is not showing here, but that's okay. So between these applications and the structured data, there's a lot to happen, right? And over the last, I would say roughly 5 years, there are a lot of technologies that have come in that really helps you process data very easily, powering those applications. So here is like the summary of that. Like it supports diverse data types. It brings in data reliability and consistency. It gives performance at scale, support for diverse workloads. So you are bringing in, all this, the data warehousing, the data science, the ML, the machine learning and AI parts of it on a single platform, that is Lakehouse. And you can use, many tools directly on top of that. So, what are those technologies which really helps, to build this Lakehouse? Here I would like to mention that, we use a technology called Databricks, which actually pioneered, this concept of Lakehouse. And they have built something called Delta Lake, which is actually a key technology in building this Lakehouse, right? So what is Delta Lake? So in cloud, you have like generic blob storages, which like where you can dump all the data, and then you have big, data processing engines like Hadoop, Spark, and things like that. But there is no support in between for things like transactions, then things like data versioning, schemas, and all those things. And that's where the Databricks guys built this Delta Lake, bringing those concepts into it, so that people can use these technologies to process this data faster and build a unified platform for processing all kinds of data and for all kinds of use cases, right? So in specific, Delta Lake for reliability, here, it brings in the ACID transactions on top of the data lakes, then schema enforcement, updates and deletes, which are very painfully manually implemented earlier, and then the data versioning aspects, where you can do a time travel, right, back into the time and look at how the data has evolved. So these features together, what it brought is reliability of the data that is in the data lake. So you can perform operations in transactional basis wherein which either the whole operation succeeds or whole operation fails, right? So they brought in that reliability. Then there is Delta Lake for performance, right? So one of the problems with this thing is, with data lakes is you have huge amount of data, so performance becomes an important aspect. So they kind of used, many key techniques like, compaction, caching, datascaping, and Z ordering to really provide a fast response, a performant engine, which they call it as Delta engine, to give a similar response as the traditional relational databases. So in a way, what they did is they brought in the capabilities of a relational database onto the data lake, which can store and process huge amounts of data using big data processing engines like Spark. So this is one of the key building block of the Lakehouse architecture. Right? So this is kind of shows how the data gets continuously processed in a health lakehouse. This is referred to as Delta architecture by Databricks. So you have data on the one end of the site. Sorry, the picture is not appearing in the center. It's a silver color database symbol. There's some problem with the presentation. So this one, right? So you get the data from multiple sources. There are a lot of sources for the data, and then you ingest into the Lakehouse. Essentially, what this is called the bronze layer. Here you store the data as you receive it, and here you kind of index it. You store based on where the source come, what source, and things like that, without really much transformation, so that you can go back to the data and look at it. So you always have the true source of the data there. Then you kind of continuously process it to get to the silver layer. So silver layer is like really the clean data, processed data, but it is not designed for any specific application, but it is just the clean data, and that represents like the source of truth for all applications. And then based on what applications you design, you take the data from the silver layer and then process it further to a specific use case or a specific application. So in this whole stuff, if you look at, the data quality is continuously increasing from the raw data that you receive all the way to the right, where it is consumed by the applications are for a given use cases. So let me stop here and see whether there are any questions with respect to whatever I told so far. Okay, so so here is I talked about what Lakehouse is. Now I'm going to talk about why Lakehouse for healthcare, right? So I talked about large amounts of data coming from various sources. So here is a picture representing the different kinds of data that is there in healthcare. We have data in electronic health records. We have data coming from wearables and devices. There is insurance claims or health claims data. There is pharmacy data. There is imaging data, genomics, then clinical trials, disease registries, and as you can see, imaging data, then health claims data. A lot of this data is unstructured, and some of them is semi-structured, and then only a small percentage of this is structured data. So you cannot use a data warehouse to process all this data, right? And then The other thing is the volume of the data is also pretty massive. Some of the studies says that, a single patient produces over 80 megabytes of EMR and imaging data, and add to that, genomics and genomics, then claims, then data from devices. So the amount of data really gets pretty massive, right? And then the thing is, you need to have all this data to build a holistic view of the patient, right? The quality of the analytics really depends on the data that you provide. And if the data is not complete, then the analytics is not going to be effective. So if you want the analytics or the insights to be more helpful, you need to consider all this data, because there is insights in each of these data stuff. So you need to extract those insights to provide a holistic view of the patient's health, right? And then the other thing is, there is a real world, there is a growing acceptance of real world evidence. I'm going to talk about that a little later in my slides. So this diverse healthcare data is the reason, why building a lake house for healthcare will be useful. And these are, the additional stuff. I talked about, using the various data sources to build a holistic view of the patient. Then in many care settings, we need real-time analytics. So Lakehouse is one that help you build, insights, or which can produce or process data and produce insights in real time. So Lakehouse would be helpful. So I'm going to talk about little bit more in the coming slides. Then also the scale, right? So if you can analyze the health data and treatment data for millions of patients, right? You can see what treatment works, what treatment does not work, and you can come up with better treatment protocols for the patient. So that's kind of the insights that you derive from the data. And then of course, you use this data to build algorithms based on machine learning, so that you can better understand the disease. You can predict what's going to happen. So you can employ those things to provide better care to the patients, right? So these are the reasons, why a lake house really makes sense for healthcare. And this is a picture, a very similar picture showing the health lake house. We have the data at the bottom, EHR, imaging, genomics, ECG, EKG, and everything in a data lake. Then you have the Delta engine, and of course, there are few associated technologies as well, but Delta Lake is one of the key stuff that that helps in building the lake house. And then, on top of that, you have applications like, precision, healthcare, preventive healthcare, value-based care, drug target identification, and deep medicine, right? So the magic is going to happen, that in between the stuff where you are going to build the processing pipelines from the raw data at the bottom to a state where it can be consumed by the applications, right? I think that's the key. That's the key here, right? So when you want to do this, right, like as you process the data, you clean the data, you reshape the data, you kind of transform the data, and then I just talked about, taking the data from the bronze layer to the silver layer. right? So once you clean the data and process the data, how do you represent the data, right? So that is an important aspect. So that essentially, is about, organizing your data, or it's about data modeling. So that's an important aspect. So you need to decide upon the data model how you want to store the data. And the second thing that is important, especially in the healthcare space, is about the terminology, right? So what I mean by terminology is, the words that the healthcare providers use to represent concepts and represent concepts. For example, if we want to say diabetes, people can mention in many ways. They can say diabetes, they can say sugar, diabetes mellitus, and so on. It's like, different languages, right? And every hospital, every provider has their own way of saying this data. And if this information is in this different stuff, we won't be able to do any of the analytics stuff, be it producing reports, dashboards, or doing analytics. So normalizing this terminology, choosing a good data model is an important aspect of building a health lakehouse or lakehouse for healthcare. So that's where the next stuff comes, which is the OMOP CDM. CDM stands for Common Data Model, as the silver data model. And here I'm talking about silver data model because this model is not specific to any use case or application. This is about representing all the useful information from the data that we want in a way that is that can be used for for different use cases, right? So what is OMOP and what is Odyssey, right? So here OMOP stands for Observed Medical Outcomes Partnership. It's actually an initiative led by FDA and the pharma companies. They formed a group, and this was based on a directive from the US Congress, where they said that, and where they asked FDA to develop a risk identification and analysis system, right? So what they said is to develop a systematic and reproducible process to efficiently generate evidence to support the characterization of potential effects of medical products from across a network of disparate observational healthcare data sources. So essentially, this was triggered by a side effect of a pain medication called Vioxx, and that led to many heart attacks and deaths in the US. So when the US Congress asked, why did this happen? How come, they didn't do the clinical trials or what? But it was found that, heart attack was such a common stuff in US, so that, the clinical trials would not catch that signal. And in order to catch that signal, right, they have to do, rather I would say the sample size of the clinical trial has to be too large, the time of study has to be too large, which makes it, almost non-viable for them. So the next best alternative is to see, once the medication is released to the market, can we have a study done on the data that is produced to find out whether, a given drug has any side effects or not. So in summary, that's what it is, right? And FDA did this experiment, and as part of that, they needed to collect the data from multiple sources like, EMRs, claims, and they chose 14 databases. They did the study. So in order to represent that into a common, they come up with this OMOP common data model standard, represented the data, and they did the study. But of course, the study proved that the accuracy was only 70%, and that's why, they said, just because of 70% accuracy, we cannot stop a medication or pull out the medication from market. So they stopped it. This happens in the between 2005 and 2014, and then they stopped the project. So as part of this exercise, there were also researchers that were involved. So they said, this is not right. We need to, further take this project. We know there is a way to make it successful, and that's when the OMOP investigator or the researchers took the same thing, and in the biomedical division of Columbia University, they set up a project called Odyssey. It's OHDSI. It's pronounced as Odyssey. It stands for Observational Health Data Sciences and Informatics, right? And they kind of continued, that work. And here is, the mission and vision of that Odyssey. So the mission statement is to improve health by empowering a community to collaboratively generate the evidence that promotes better health decisions and better care. So the key word is to generate evidence from real world data, right? And when we talk of real world data, the data that is any data that is outside of a clinical trial is called real world data. It is in the everything, a lab result that you do, the information that is collected in EHR, and all those things are called real world data. And the evidence that is generated out of that real world data is called real world evidence, right? So their mission is that, and the vision is a world in which observational research produces a comprehensive understanding of health and disease. And this is a non-profit organization. There's a community behind it, a very vibrant community. And on the right-hand side, the picture shows, who are all the Odyssey collaborators and the Odyssey data network. So they are dealing with real-world data, and they took the OMOP common data model and they further expanded it, from medications to cover, lot of other data as well, right? So that's what it is. And here the colors are not showing up well, but here is how the OMOP common data model looks like. And as you can see, there are the tables which are very well defined. I'm just putting a picture, but there is a schema well defined. You can go to the Odyssey website and look at it. The other big advantage of this data model is, the standard terminology. I believe, they have one of the best terminology, and the other thing is, they have cross-mapped their terminology with more than 100 other standard terminologies. So when I say standard terminology, there are groups or industry consortiums or sometimes government who form to standardize these concepts. If you have heard about things like ICD-9, ICD-10, SNOMED, so these are all standard concepts, and there are many such standard terminologies. And as I said, this is one of the most comprehensive terminology from Odyssey, which covers a pretty wide amount of concepts in the healthcare field. And as I said, it provides cross-mapping to 100 plus standard terminology. So using this, if we can normalize the information that we get from the raw data onto, and then represent using this common data model, then it becomes a lot easier to carry out, analytics or use it for any use cases. So this is one of the key elements of, building a health lakehouse. So here I'm coming to the more specific of what we did or what we are doing at G Healthcare in PCS digital business. So I talked about different types of data, right, like imaging, wearables, devices, EHR, claims data and everything. So are we building a health lakehouse that include all this data as of today? So the answer is no. We are focusing on a smaller subset of this data specifically to the business in which I'm working on, which is patient care solutions business. This is a business primarily in the patient care devices that is used in critical care areas. And when I say critical care areas, I'm talking about ICUs, operations rooms, intensive cardiac care units, labor and delivery units, and so on. And here, as you can see, it's called critical care areas because the health of the patient is very critical there. It's actually a life and death scenario. You can imagine in an ICU, right? So the timeliness of the intervention or treatment when the patient's health goes down is very important, right? So that's where, in ICU, if you look at it, the patient is hooked on to different devices like patient monitors, ventilators, and so on. So we have data coming from those devices in real time, and it's a streaming data because the data is coming like every second or every few seconds once the data is coming. For example, ECG flows continuously, right? And you have, and it's 24/7 because, in ICU, you cannot stop at at 6 o'clock or 8 o'clock, right? So it is life critical. So that's the space in which, we work on. And we felt that building or employing this lakehouse architecture for this really helps for the care providers who treat these life critical patients in an ICU or in a labor and delivery department, right? So further to show the criticalness of it, that's point number one. And the second thing is, if you get to learn about that patient condition or think that the patient condition is deteriorating much earlier, then the care providers has a much longer time to provide that care to the patient. So this is a paper in British Journal of Anesthesiology, where they say patterns of unexpected in-hospital deaths, a root cause analysis. So they have taken a specific pattern or specific cause here. So this graph here shows the oxygen content, then in the blood, then the carbon dioxide content, and then the respiratory rate, right? And here, if you look at it, towards the end, there is a sudden deterioration of the patient, right? For example, the oxygen content is falls very sharply, because of which the respiratory rate increases because you need to get more oxygen, and then the carbon dioxide then suddenly spikes up, right? So there, when that stage is reached, the care providers has a very small amount of time to save the patient. But what this slide is showing here is, if you look at on the left hand side, right, that is probably where the onset of potentially mortal event happened, but the signal is deeply buried in lot of data across multiple devices and things like that. And if they are able to catch, they have the care providers have lot of time to save the patient, but instead what happens is they get to know only towards the end when the alarms on the devices starts beeping, and they have to act fast. And this is where they make a statement in this paper: potentially fatal false sense of security may exceed sometimes 12 hours, right? And this is what, like if we can build proper analytics, we can really, help care providers or inform care providers much earlier of such incidents and help them, give lot of time in saving the patients, right? And this is one case, and there are other cases where I have heard that, like even a 10 minutes early warning to care providers can really help saving the patients, right? So this is what is at stake in critical care areas. So this is, this slide I just put it so that, to explain what care providers go through in an ICU kind of setting. So there are patients because of different complications, and these are many of the things that they need to manage. And these are all, clinical terms, so I don't expect you to, follow that, but just gives you a thing, how much of workload is there on the care providers in the critical care areas, and helping them provide, information early enough to treat the patient goes a long way in saving patients' lives, right? And not only in ICUs, this is again another paper from the British Journal of Anesthesiology, where they say that it's not just in the ICU settings, but even in the wards, if you are getting data continuously, there also you can help, save the patients, right? Today, there are technologies in terms of wearables where, you can attach the patient to and you can get continuously data, but we need someone to act or look at the data, and it's impossible to have, a care provider looking at that like continuously, and this is where, we need to build that analytics so that, we can provide the information to this, that this information can be monitored and this information can be provided to the care providers at the right time. So, yeah, so this is again, stressing on the importance of health lakehouse here. So we had what happened on one side, and then what will happen on the other side. So what happened usually, it's the area where, your analytics, business intelligence, and reports kind of help, right? That's the traditional data warehousing concept. And then in terms of what will happen, it really falls in the area of data science, AI, ML kind of stuff. And traditionally, these were two separate platforms, and the data, the information was not being able to, reuse across these two stuff because the tools were different, and bringing over data was very painful. We had to build ETL from one system to the other, and then the data was not in sync. So all these challenges. So the Lakehouse data platform really bridges this divide between these two, bringing all these use cases to a single platform. So you can really do everything on this single platform, really speeding up these things, right? So building a health lakehouse, what components you need. So on the left hand side, it shows a list of things that is required to build any, like a data lakehouse for any area, right? So you need a data lake, which is usually a cloud blob storage in any of the public clouds. Then a powerful engine to query the blob storage, like a Spark, and then the transaction layer to provide data reliability and consistency. I talked about Delta Lake. And then ETL and data cleansing workflow. So this is where, you have the technologies and everything, and if you are building a data lakehouse for anything, this is where, you will build that ETL pipelines. Security, data integrity, and performance. Again, these are the stuff that are provided by the technology advancement in the last few years. Here in Databricks, has the Delta engine. Then all these things, once it's processed, it needs to expose through a well-defined API or a good IDE, where people can leverage it, and that is where a SQL interface and then things like notebooks, Jupyter notebooks, all those things comes important. And then there is this unified governance, right? Especially where data is sensitive. For example, the patient health data is sensitive. You cannot let the data go in public. It has to be seen by people who only needs to see it, like providers and things like that. So we have to be careful in terms of that data. That's where one is centralized governance, but that means who has access, who sees, who can download, things like that. Then when you have huge amounts of data, you need to know what data is there. So a good search and discovery mechanism is important. And then as you process the data, right, you need to understand where is that signal or where is that insight coming from. So tracing it back all the way to the data source becomes important. So these are some of the things that are provided by unified governance, and Databricks has a technology called Unity Catalog that is part of in their Lakehouse technology that provides this. So of course I'm specifically talking about Databricks as the stuff, but this is not the only technology. There are other technologies offered by other vendors, but since we are using Databricks, I'm talking using the terminology, but the concepts remains the same, right? Then what are the additional things that we need to build a health lakehouse specifically? That's where I have put things on the right hand side. So today, if you look at it, we have the data from EMRs and claims coming in HL7V2 and fire message format. So you need to have a good parser and a fast one, highly scalable parser, because we are talking about large volumes of data and we need performance. I talked about the terminology, and that's where OMOP, common data model, is helping. And we need terminology mapping tools, right? So when we take data from a hospital, it is in a different terminology. So how do you map it to a common terminology like OMAP? So we need to have those mapping stuff, right? And since the concepts are huge in number, it becomes too time consuming and probably practically not possible to map all those concepts. To give you an example, right? One of the hospital which we are working with, their pharmacy has roughly 5,000 medications. So, and it is in a proprietary terminology. How do we, map that to the standard terminology? So that is where, you need to have mapping tools. And ODC, community has come up with some tools for that. It's decent, but not enough. But there may be other things that help. But finding a good mapping tools, makes your healthcare lakehouse or health lakehouse things easier. And you need to have clinical and terminology expertise, right? See, if you the data is represented in various forms, and it varies from provider to provider, one healthcare organization to another healthcare organization. So when you're transforming the data and representing that in a common data model, you need to get the semantics right. And if you don't get the semantics right, then it's becomes garbage. Worse, you can create false insights which may harm also. So it's very important, and that's one of the key stuff, right? if you don't get the semantics right, it won't help. So you need to have that clinical and terminology expertise in the teams when you're building that health lakehouse. And the other thing is, data quality management process, which is like when you're ingesting megabytes, gigabytes, and petabytes of data, you need to ensure that you have the quality of the data. So you need to automate that process, and then you need to have the dashboards that kind of can look at and see how the quality stuff looks like. And you also need to have a process in place. If something goes wrong, how do you act quickly? So Health Lake is not like a static entity. It's like a continuously running entity. It needs those operations and things like that in place, so that you quickly fix them when things kind of are not working. So this is what is required, and with this you kind of with these tools and expertise, you kind of build those ETL pipelines which can process the data and improves the quality of data, taking it through the bronze layer, the silver layer there, where and you represent that with the OMOP common data model. And depending on the use case, you further build pipelines and create the goal tables for that specific use case. So you have kind of, if you want to say, you have one data model representing all the data, and then you have a data schema for each of the application or the use case as the goal tables or the goal this thing. So this is just the screenshot of the Mural Insights. It's an application that GE has developed, which is powered by Health Lakehouse that we have built. And this is a dashboard built on top of Tableau. So Tableau has, you can connect to the Databricks Health Lakehouse that we have built from Tableau directly and produce these dashboards. Just to this thing. So coming to this thing, towards the end of this presentation, I just want to quickly touch upon the lessons that we have learned while building our Health Lakehouse. So there are quite a few here. I'll just quickly talk through this. How am I doing on time? Is it okay? Okay. So the first one, while Health Lakehouse technology solves many of the hard challenges, and that's a very true statement. Actually, building applications has become a lot easier with this Lakehouse technologies, like like Delta Lake, then Unity Catalog, all those things. So there are a lot of things that we used to do manually, but now right away offered by these tools directly. So really makes things easier. But that is not a silver bullet, especially when you're building a Health Lakehouse. Good data modeling and common terminology is key to the success of a Health Lakehouse. I talked about that. OMOP CDM has one of the best standardized vocabulary. I talked about that. Then what you need to know also is, healthcare data is really, really messy, right? You have to work with source data custodians to ensure the right semantics is not lost in the translation, and that is time and effort intensive, and this is where I said the clinical expertise and the terminology expertise is required. Automation of terminology mapping from source data to OMAP vocabulary is a must, especially if you're dealing with multiple data sources, or if you're adding more and more data sources. Automation of this terminology mapping is very critical. Performance optimization of real-time pipelines is not easy. So these tools are great. You need to have a good understanding of how it is built, how it is working underneath. Otherwise, you end up building very inefficient pipelines, very time-consuming and costly to run. So we ran into that issue. If you naively implement a pipeline, it's not going to give the performance. You need to have that understanding of how the systems work beneath. So PHA is involved, so data governance is critical. So you just cannot get the data and keep it open for everyone access. It has to be only on a need basis. Lakehouse technology is not a substitute for good data ops practices, right? So data ops, I have a reference in the next slide. So it's a combination of agile practices from software world and lean from the manufacturing world. So those practices are very important. Otherwise, it's very difficult to efficiently operate a big data system like Lakehouse, right? So pay attention to that. OMOP CDM, it's primarily, those tables are geared towards EMR data and claims data. It has a long way to go before it evolves to support all healthcare data. So there are a lot of work groups continuously, evolving the CDM, and hopefully one day, we'll have, a model that can represent, all information. So right now, we build custom stuff for things that are not covered in the OMOP data model. So, and then the last one is, this is in terms of, I talked about building a holistic view, but today that is still a distant challenge, because a patient's data is really in multiple databases, and getting all of them together is a challenge, right? So today we continue to have those, like isolated data, but still, building that health, like building even from a single organization, these big data processing platforms like Lakehouse is going to be useful. So, and then here are the references. So these are really, really, in my view, very good references. It imparts a lot of knowledge, especially if you are building a health Lakehouse. So I'll share this presentation later, so you can go through these stuff. One of the things I also would like to call out here is, you see that Stanford Medicine Clinical Data Warehouse Reimagined, or STAR OMAP, specifically Stanford Research and Data Repository. They were earlier built their analytics on top of using data warehouse technology, but in the last few years they have migrated to this OMAP common data model, and they have built their data repository on GCP, Google Cloud. They have used BigQuery. BigQuery is again, another implementation of the data Lakehouse pattern. So that also, is a good resource to learn about healthcare, how health lakehouses are built and things like that. So I think that concludes my presentation. So any questions? Okay, all right, thanks.
Thank you so much, sir, for the wonderful presentation. So we could understand the relevance of data lakehouse in healthcare unit, and also thanks for the case studies and the references. So next, I would like to request Nasreen ma'am to give a small token of love to Satish sir. So we are moving to the next topic of our talk show. So the topic is Data Lakehouse in Azure. So it's my privilege to invite Mr. Srikanthan Shankaran, Senior MTC Architect, Microsoft India. So Srikanthan Shankaran is a Senior MTC Architect as he is in Microsoft, and he's working for 16 years and taken up with multiple roles in Microsoft, and also he helps Microsoft customers and partners in digital transformation journey by leveraging Microsoft Azure. So sir, please come to the stage.
Just give me a moment before we download my deck onto this machine. I think thanks so much, Mr. Satish. I think it was quite enlightening. A lot of new perspectives I got, and particularly the emphasis in the healthcare domain and how it's relevant and how data lake fits in. I think very well conveyed, and thank you so much for that. Many of the aspects that I wanted to cover, I think Satish has covered some of those. I'll try to sort of make sure I gloss over those and not really make a repetition of those. I'll try to cover things which probably came to my mind as he described it, and probably where it will help fill certain gaps, and then hopefully you folks get a full picture of it. That's the first slide.
Okay.
Right.
So you need the whiteboard also.
Let me see. There's a pen out there. No? I'll just go there and write. Should that be the case? But let's see. I'll later on in case I need it. It's fine. And how much time do I have now?
I have 1 hour. So 40 minutes, 1 hour.
Okay. Hi everyone. So I think as she introduced, so what I'll be talking about is how Azure helps you in your endeavor to build a data lakehouse architecture, and what are the services and technologies that help you in that particular journey. But before I did that, I just want to take an opportunity to give you perspective what was offered on the data stack from Azure. I'll try not to spend too much time on the rest, because easily we can take a couple of hours, and at a film don't intend to do that. I'll try to focus upon those aspects that are relevant in the flow, which applies to the creation of the data lake architecture. So what you see on the left are all the different data sources. So we have data sources in other clouds, and then you have some data sources inside your data centers. Okay, and then it's a combination of structured, unstructured, and semi-structured data. I think unstructured, we all know it's all about video streams, and then you have images and all of that. And then semi-structured is typically where you have applications which spit out CSVs or JSON documents, or probably the ORC or Parquet files or something like that. And structured is all the, you can think of the SAP HANAs and then the Oracle databases or Word. So that's what I actually refer to. So you need to have, so the data resides in multiple places. They could be in other clouds, they could be in your data centers, and then you need to have a mechanism to pull all the data. So in the context of the Lakehouse, I think Satish already mentioned that, this is all more relevant in the big data world, where we are not talking of the scenario which was prevalent a couple of years back, probably a decade back or whatever, where you had enterprise systems, you had structured data, and all the analytics that was performed was using a data warehouse, because it was structured data right from end to end, okay? And then probably all that it did was probably aggregate and sort of slice and dice the information and present it, and then probably help yourself on building some pipelines with which you could build machine learning models as well. But in the big data world, you have sensors which spit out, gigabytes of data in a snap of the fingers. Okay, so obviously you don't want to dump all that information into data warehouse, because data warehouse data store is extremely expensive. So obviously you don't want to sort of have some dumb data lying there, which is better probably stored in a data lake. Okay, so what I'm also trying to get to is that you need to have a technology which helps you pick up data from different source systems, be they structured or unstructured. So that's where Data Factory in Azure really helps you do that. But again, if you have Databricks, it has connectors to various database systems as well. So you can actually choose between Databricks and Data Factory. And Data Factory gives you a low-code, no-code way of doing it, which means that I don't need to write code to connect to an Oracle database or connect to SAP HANA. It gives you a connector out of the fly. You just sort of drag and drop into the pane, and then you just visually compose a pipeline saying that, hey, this is how I call that RRC or BAPI. Okay, and then I get the information, and then I need to translate it on the fly into a JSON document, which or a Parquet file which goes into the delta table in data lake. Okay, so we can actually ask the tool to automatically map certain columns if we have the source and target schema. As long as the names are sort of they are actually intuitive and probably they are similar, it will automatically do the mapping for you, and then you can actually override it and say that no, I think this you got it wrong, and then you go ahead and sort of make those corrections along the way. Actually, I would have loved to demonstrate. In fact, I hadn't planned to show the deck at all. I wanted to show an end-to-end demo itself of the entire Lakehouse, how you actually start from scratch and end up with it. But unfortunately, I couldn't actually project from a laptop, so you'll have to live with the deck, and I'll try to convey the story to the best extent possible. Okay, so yeah, coming back to the Data Factory again, I told you that it is a managed data ingestion and transformation pipeline with which you can connect to numerous data sources, and then you can dump the data. So like Satish mentioned, the first thing you do is typically that you don't want to call the source systems again and again. Okay, let's say you got some data, and let's say you transform it in the first step, and say because you had some requirements in mind, and then you sort of dumped the transformed information out here. And a couple of years down the line, you realize that, hey, for purpose of machine learning, I ought to have the attributes which we discarded in the process of transformation. So obviously, you don't want to go back to the source systems because they're already sort of under load because of all the transaction systems. So you don't want to periodically call the same data and again. So which is why typically you'll actually pull the data once, okay, and then you dump it into in its raw form. It could be CSV or Parquet or JSON, whatever it is, and then that's where you call the bronze store as he described it. Okay, once you do that, you need to cleanse the data also, because obviously it came in the raw, and data from sensors, probably it's, at a particular time a sensor acted up, and probably certain columns of information were blank. Okay, so when you want to build a machine learning model, you can't afford to have blank values, because when you build a model based on inconsistent data, the kind of interpretations and kind of accuracy is going to go for a toss. So obviously we make sure that depending on the kind of data that I have, I may need to impute certain values, do some kind of validation, do some schema checks along the way, and make sure that I have a cleaner version of the original data. So that's typically what the silver is. So that's not, though that's not the only definition of what a silver is. The Medallion architecture talks of bronze, silver, and then a gold. So bronze is the raw data as you actually pull from various data sources, and then silver is where you probably cleanse the data and then do some kind of schema validation as I just described. Okay, by the way, just a couple of other things which you can do with the with Databricks is that you can also do schema evaluation, for example. See, when you start today, you say that, hey, the source data has 5 columns, okay, and then so happens that because they changed the sensor, or probably they upgraded the sensors and the associated instrumentation, you find that it sends about 10 attributes right now. So you don't know what to do with the rest of it, okay, and your pipeline should not fail just because, hey, I expected 5, but you're giving me 10 attributes. So there should be a clean way of handling all of those. So probably what you could do is you can ask Databricks to say, hey, you can ask Databricks to determine that if I get more attributes, do I just want to take that in, okay? And it will not sort of reject it and throw the data away, because data is sacrosanct. You don't want to throw it away just because you got some extra data. Or you can say that, no, I need only 5. Probably then you can say you want to reject it, and then probably raise an alert saying that, hey, I think something wrong with the data, someone should take a look at it. But in most probably the cases, you will absorb that information, and then you let Databricks determine and evolve the schema as you go along. So what happens is that on the fly, it creates those additional columns in your delta table or in the Parquet or data store. And then for the older data, those columns will be blank. Okay, so that way it's able to very cleanly manage all those kind of variations to the data within known limit, within boundaries. You don't want it to go sort of break loose, and sort of take everything that comes its way. So obviously you need to temper what you actually do with that information, and make sure that within a certain ambit of freedom, you're able to absorb additional information, and then you store the data. Yeah, so again, coming back to this, we had bronze, and then you have the silver data store, which is probably a relatively more clean version, and then the data is practically valid, and then it's validated, blank values have been imputed, data probably, yeah, I think that's about what you do in the silver stage. And then when you come to the gold stage is where you want to actually base your analytics upon, okay, or probably the machine learning upon. So you'll not have a one-to-one mapping in the gold store. Typically what happens is that I have 10 tables, let's say in the raw data store coming from numerous sources. Probably I have 10 here in the silver as well. But then when it comes to the gold, I need to probably create different views of the data, probably segment that particular data to sort of light up different scenarios. For example, you're in a retail kind of a scenario where you want to do customer segmentation, then probably you have customer information coming from salesforce.com, and then you have transaction information coming from SAP. Okay, and then you need to combine this data set, create a new data set altogether, which is meant to sort of drive a particular use case that you have in mind for analytics or machine learning. So that's how typically it goes through, okay, but not necessarily etched in stone, but that's usually what the flow is about. So all of these steps that I mentioned about creating the bronze, silver, and the data and the gold data source for the Medallion architecture can be done using data factory pipelines, or you could use Databricks as well. So in fact, last couple of projects, they all been on Databricks, and then we sort of, they were Python and Spark developers, and then they wanted to sort of piggyback on that. And it's also so happened that Data Factory was not available in that particular region of Azure, which was UAE actually, and which is why they actually doubled on Databricks, and then all the data ops and the MLOps were implemented on Databricks itself. Okay, so far so good. So we have all the information in the data lake. And yeah, the other thing to mention is that probably in the bronze and silver, you're talking of CSVs or Parquets. In the silver also, you could have a delta table. So I think Satish already mentioned that, hey, I get the data in these formats. Okay, at some stage, I want to say I want to have a delta table. So that brings in the notion of the Lakehouse architecture. So Lakehouse architecture, I'm sorry if I don't want to repeat what he said, but I'll try to mention a couple of things which probably add some more meaning to what he said. So data resides in the data lake. Okay, it's in the Parquet format. And how do I query it? So let's say I want to serve this data from a reporting tool like Tableau or Power BI. Probably it's suboptimal for us to point it to a partitioned Parquet kind of data on the data lake. So it's not going to be performant. It doesn't know how to sort of, it has parsed all of that, multiple Parquet files running to several subfolders and all that. So not very efficient way to ask a Tableau or Power BI to sort of serve that information. So which is what you do is that you actually need to slap a schema on top of it. Okay, so you create a schema. For example, in Databricks, you have the Hive meta store where you can actually create a schema saying that, hey, I have my data in the raw here, and then you actually run a T-SQL, ANSI SQL command, which is going to create a Hive meta store inside Databricks. So next time you run the query, you will actually query as though you're querying a table. Okay, so that's the magic. So data is in Parquet, partition, and in the data lake, but then you're able to query it as though it's some kind of a table. Okay, and so that's where actually becomes extremely powerful. You are able to have this particular table or a view as the sort of endpoint which you provide to Power BI. So Power BI just queries as though it's a table, and magically all the sort of data appears in the most optimal way. You're able to run heavy aggregation. Imagine aggregating data on the fly on data residing in the data lake. It's going to be very suboptimal, isn't it? So that's where, I mean, all the data lakes in AWS and Azure, they support the notion of push-down predicates, which means that you partition the data, even though it's Parquet, and then you have all the columns that you typically have in the where clause of a query, you might have partition on that particular table. So when you run that particular query, instead of Databricks loading all the data, and then in memory you sort of filter it, you don't have to do that anymore, because push-down predicates let you even when you query and pick up the data, it's based on those filtered values. Okay, so that's where actually it's extremely powerful. Yeah, so at times I try to cover different aspects. I need to come back to the original flow. So which is about serving this data effectively to different analytics tool, which is Power BI in the case of Microsoft. Feel free to sort of interrupt and ask me any questions. Otherwise, I'll just keep going on with this particular, with the talk. Okay, I'm just trying to think, is there anything that I need to cover? Yeah, other thing about Lakehouse architecture, which I want to supplement what Satish said, is that in the traditional world, we used to have all the ERP systems and CRM systems. We had structured data coming in, and then it seemed logical that we'll actually build the warehouse in data warehousing solution. Okay, but then with the coming up of all the big data, I already told that we have so much of data. You obviously don't want to dump them in a data warehouse and pay unnecessarily for a storage, which is much more expensive. Okay, but had it not been for like a Lakehouse architecture that Databricks support, what it would entail is that I create all this the bronze, silver, and gold data stores, but still it is Parquet and tables and all that. So I can't expect the data warehouse folks who don't understand Spark at all. Okay, so why would they learn Spark just because, hey, Adam, you don't have data warehouse anymore, have data here, data lake, please help yourself. So obviously they'll throw up. I mean, they said it's not acceptable. They only know ANSYS SQL or T-SQL. So the technology of Lakehouse should also permit the right roles or people to use the technology of their choice. So with the Lakehouse architecture, with just the SQL expertise is all that they require. So Databricks has a Spark kind of compute capability. It also has a SQL analytics, which has actually come up in the recent years, where you actually run T-SQL and then you're able to build your SQL warehouse on top of it. So I think that's a very important thing that I want to convey. Just keep that in mind when you think of what a Lakehouse architecture is, why it is different from what just a data lake, and how is it different from a data warehouse. So I think these are some key things which need to be kept in mind. Okay, so let me think what else I should talk about. Yeah, the other thing is, I told you that Databricks is definitely one of the solutions where the Lakehouse architecture could be implemented, where you store the metadata in its high store, and then the data resides as Parquet. So Delta table is nothing but Parquet with an additional layer on top of it about logs. He mentioned about the transaction logs, the fact that you update data in bulk, and then how do you so let's say the target system to which you fed this information conked off, okay, and then you need to regenerate the data. So in a typical system, you'll have to go to the audit logs and sort of do some kind of song and dance. But with the Delta table, you can say that, hey, get me all those records as on that particular date. You can give a timestamp and say that I want to actually do a time travel back and then pick all the information up, and then you're able to feed the system again. So that's kind of magic and sort of music to our ears. And all that it does, all this data coming off something like a blob store or a data lake, so it's very inexpensive store, you're able to do all this magic. So I think a lot of things to take away there. Okay, so so all those things you can do with Databricks. Azure, we also offer something called Azure Synapse Analytics, which lets you do the same thing with the same kind of technologies. So a bit of history here, Synapse, I just realized I'm still on the slide one, and but probably will go easy on the rest of the slides, and most of it I've already spoken here because this diagram sort of completes the end-to-end story, isn't it? So we talked of pulling all the data and dumping into the Lakehouse, and then we spoke of Databricks, how it can actually helps you achieve this particular aspect. And then I'm talking of the other tool, which is Synapse Analytics, which helps you do the same thing. Like with Databricks, you have a SQL dedicated pool. You also have something called the Spark pool as well. So historically, I mean, it was actually previously called a SQL data warehouse. And it was intended for Microsoft shops where customers have been on SQL, Microsoft data warehouse technologies all the while. And then we wanted to see, hey, how could we equip such organizations who want to leverage their skill sets in Spark and who want to have a single umbrella within which they're able to run different kinds of workloads. So after that, we actually brought in Spark. So as a part of the Synapse Analytics rebranding and bringing a host of additional capabilities, it's actually limitless analytics engine, which means that you can just dial the knob to the extent that is required to run your compute capacities and then your storage capacities as well. So a couple of things that it offers is that definitely it offers a data warehouse that we always knew it used to have from the past. It offers a Spark pool, which means that all the transformation, whatever you do with Databricks, we can actually do it from Synapse Analytics as well. But there is a slight difference. So the Spark engine, obviously, Databricks is from people who actually created Spark, okay, and then they actually have fine-tuned it, they have actually optimized it, they have the Photon engine, is blazing fast and all that. Synapse Analytics uses the open source version of the Spark engine, and then they embellish that further with the
also has a SQL analytics, which is actually
very good
come
and
up
very
in the recent years
performant.
where you
You
were
can't just compare them. Probably may need to do a load test between the two to make sure that for the workloads that you are evaluating them for, which probably gives you better results. Definitely, Databricks will really shine. But and there are a lot of reasons why you may want to go to Synapse Analytics, because apart from just the Spark engine, it gives you things like an integrated tool for Power BI. You can just plug in all the other services in Azure which are required in the process of building and deploying a Lakehouse architecture, and all those things just fit in. For example, I mentioned Data Factory. So this is available as an Azure service by itself. So without Synapse Analytics, I can create a managed data pipeline and then have all my integrations handled. But if I'm saying that I want to look at Synapse Analytics as a one-stop shop, it has something called Synapse Pipelines, which is actually an extraction of what Data Factory is, okay? And then, so right from within that, without having to go to a separate resource, you can just say, let me use a pipeline feature of Synapse, and then you create all the integration scenario that I spoke to you about. So you have something called Microsoft Purview, which is equivalent of Apache Atlas, so the same kind of data catalog capabilities with the full, with the capability to sort of have lineage tracking auto classification of all the information. He mentioned about PII information, how important it is to classify the data. So, so unless you do that, people who are consuming will be blissfully unaware, and probably very sensitive data would likely be shared with external third-party providers. So it's very important to have an overarching governance tool, which is what Purview is, the one on the yellow on that written vertically there. Okay, so that's about what Synapse Analytics has to offer. By the way, it also has something called a serverless pool, which means that for sporadic and ad hoc workloads, you don't want to sort of have a dedicated pool which is constantly burning, and then you sort of end up paying for it. So if there are occasional burst loads, and then you want to do something like build an application quickly, which you can definitely make use of the serverless pool. And in fact, the Lakehouse architecture can be built using serverless pool. And then the ability to sort of talk to a Delta Lake and all that is available in the serverless pool. The dedicated pool doesn't have it. Probably sometimes it's going in the future it might have it. But just a minor call out in terms of how they differ from one another. Okay, so that's about Synapse Analytics. I don't know anything what else I should cover here on this particular slide. And the data lake, I think I just want to tell you that, it first came as Azure Blob Store, which is equivalent of S3 buckets and all of that. At some point we said, hey, we need to support big data workloads, because the original blob store wasn't very conducive for storing data hierarchically. And the way it was actually stored in Azure is, even if you have a folder, a subfolder structure, it was almost like saying that, hey, subfolder name slash, subfolder name slash, and then the file name. So it wasn't actually a nested structure. I mean, originally when it was conceived, that's how it was. So all the things, when you want to actually unplug data from somewhere in between the hierarchy and push it somewhere else, it meant a regenerative sort of traversing across the entire path, and then extracting the information and then pushing to the target. So in a big data world, obviously you can't live with those kind of limitations. So very quickly we realized that, and then we sort of brought the data lake capabilities, which makes it extremely conducive for extremely performant and high performant requirement in the big data world. So it actually supports all of this. You can actually have POSIX-based security ACLs being applied on all the data at different folder, subfolder structures, and highly conducive for big data workloads. In fact, the go-to thing for us when it comes to doing big data analytics. Okay, so I think that pretty much covers the analytics part. And just an offshoot of what I just said is that with the data you have, you want to analyze it based on what you already have. Okay, but you may also want to predict things, saying that, hey, I have all this, can you tell me what will happen to me? Numerous examples Satish gave. So which is where you need to plug in machine learning. So with Synapse Analytics, you can actually plug in the, you can actually integrate the Databricks, where you can run all the machine learning jobs that you have. For example, I mean, you all know that Databricks has the machine learning library that we provide for Azure. So you can actually have all your machine learning models built right within Databricks using all the frameworks like TensorFlow, PyTorch, all that you're comfortable with. You can actually do all of that. And the same thing can also be done something called Machine Learning Studio of Azure, where you can actually, it's the native, it's a Azure first tool with which you are able to, first party tool with which you are able to build all those models. So that's what is represented in that particular diagram out there. And it also has things like AutoML, which means that, so let's say I'm new to the data science world, and then and there are so many algorithms that apply to that particular space, and it's hard for me to decide what I should be using. So which is where you'll ask AutoML to do all the grunt work for you. It'll just go off and sort of run the experiments on all those algorithms and tell you that it'll do a sort of a scorecard view, saying that, hey, I ran all of this, and this is the best model that you should use. So it takes away a lot of pain from doing all those things yourself. It saves you a lot of time and effort. It also has a code-first approach where you can actually write Jupyter notebooks and write all your machine learning models as well. So let me not deviate so much, but I just wanted to give you a perspective of that as well. Any questions on this so far before I move into a bit more detail? Yeah, so on this slide, I think there are some points which are called out, which are pretty obvious ones. I try to emphasize on those which are not so obvious till I actually start using it, and then realize why certain things are important to convey, which I already did. But in terms of the other easy to spot kind of differences, I think the nature of data. So in the data warehouse, typically you have data from relational systems and then operational databases, whereas in the data lake you'll have pretty much everything under the sun sending to it. Okay, it could be sensors, it could be your application logs, it could be Twitter feeds, for example, when you want to do sentiment analysis. Okay, so that's what comes under the data lake. And the schema, so obviously you need to, for a data warehouse, you need to create a schema first and then a table, and then only you actually pull data into it, and then you perform analytics. But here you can actually say, let me dump the data and then use Synapse Analytics code-less editor to actually look at that Parquet, the delta table. It gives a structure for you, okay? And then so all those things are done automatically by those tools. So you can actually do the schema creation as an afterthought. It's not mandatory to have it. So either you can say I want to aggregate based on the table that I create in the Hive catalog and query based on that, or I can say I can do a sort of ANSYS SQL to load data as a row set from the Delta Lake and then do the aggregation. So it's your choice entirely. Okay, so that's creating a table structure is not mandatory because a Delta table has sufficient information and then you're able to do all of that. The price performance, obviously, to store everything under the sun, data warehouse is going to be expensive because it's not definitely cheap. And then, but whereas a data lake, it's meant for that. It's meant to be a data swamp, though I hate to call it by that name. So it becomes a swamp in many cases where people just dump everything and don't know what to do with that information. Okay. Data quality. So in data warehouse, you need to put in curated data. You can't say I have a sort of a bronze, silver, and gold. I sort of have various versions of the information. You can imagine how quickly it will be so expensive and so it is such a bad idea to do all of that in the warehouse. Ideally, you'll have a data that is highly curated and which is meant to be consumed directly for analytics and machine learning purposes. Okay, so whereas in the data lake, I think we just spoke of the Mendelian architecture where it could be extremely raw to the one that is extremely fine-tuned and optimized and sort of purpose-driven for a particular use case. Users for data warehouse, they are business analysts, whereas data lake, like I just spoke about Databricks and how different personas can work. Data engineers will work on the Spark side of things where they build those pipelines, okay, and then they write code in Python or Scala or R or whatever. Whereas when the same data in the Delta table can be queried upon by the data warehouse or those analysts, and they can use ANSYS SQL to actually do all of that. So that's the that's how it lets multiple personas work on the same data and use the skill sets that we are equipped with. Okay. I think the last point is pretty obvious, so let me not belabor on that. Let me see how I'm doing on time. Okay. I just realized that some of these slides, they sort of echo what has already been discussed. But just for sake of completion, let me just go through these. My apologies if we are repeating certain things from the two presentations so far. So the key principles here is the fact that all the data can be stored out here, okay, and then you have raw data, you have curated data, and then at some point you have a delta lake where you give structure to all the data underneath, and then you are using for different scenarios. So the different scenarios are, one is you want to have a curated data lake, which means that the Mendelian architecture where you want to refine the data, curated, create different segments of the same information, which is meant to power different use cases. So you need those capabilities through the Spark engine. And then you need SQL analytics for all the data warehouse folks who understand only that language and they are sort of familiar with that side of the world, and they use those tool sets with which they are able to query the same data in Delta Lake but using ANSYS SQL. Okay, and then we also have data scientists who feed off the gold data. They do feature engineering on that information, and then they sort of do those experiments using Jupyter notebooks. So on this, I just wanted to say that when you actually perform your hackathon, I realize you are not going to the machine learning side of things, but at least things like data ops and ML ops are extremely important. So I'd be very happy if you folks actually implement a data ops pipeline also as a part of your hackathon, apart from just writing the code. See, the difference between data ops and DevOps is that DevOps is just about code, like Satish mentioned. But then in the data world, it's not just about the code, isn't it? You write your Databricks workbook in which you use Python or whatever language you're comfortable with, and then you have some kind of schema or data with which you need to unit test and sort of make sure the pipeline works as expected. So the data ops is the ability to sort of have a DevOps kind of an approach to both code as well as data put together. Okay, so and then you should be able to take this code and data and then be able to push it to every higher environment to make sure that you have the staging and then you have the production, and then you know that it works fine. And every time there is some kind of a schema change, you need to go back to the drawing board and then you sort of create a new data ops pipeline. You sort of run the data ops pipeline, making those changes, and then make sure you propagate that in the proper way rather than just randomly sort of dealing with data as well as code as though they are totally separate. So that should not be the case. Talking of that, so instead of repeating what we already discussed, I thought I'll just talk certain things which is slightly off topic. But the fact that I would also want you folks to use Git integration in Databricks. So if you are using GitHub or GitLab or whatever, so it'd be good for you to get started on data ops. You need to have a source repo where your team can actually check in your code and manage all the version controls. So What is the repo that you intend to use for your hack, if I may ask? It'll be GitHub? Okay, and that's good. Yeah, so you can actually create your CI/CD pipelines. So all the, you would be aware that till recently we didn't have the ability in Databricks to have a collaborative workspace. Okay, it's almost like saying that you have a master branch, okay, and then this is where all my pipelines are, and then you realize you need to build a new feature, and then you create a new feature branch out of it. So it wasn't possible till recently, I think probably recently is about 6 or 8 months probably, where that collaborative project feature, workspace feature was not there, but definitely exists now. So just like how you would actually use Eclipse or you would use VS Code, with which you're able to actually handle all these activities as a developer, where you create a new feature for yourself, okay, and then you check in the code, okay, and even as you check in, you actually you get the code reviewed, you run all those unit tests, okay, and then it goes through a build validation before someone okays that code, and then it merges and does all of that. So all those things can be done with the Databricks notebooks as well. So those capabilities are integrated into the whole thing. And the other thing which is very important, which I'm talking from my experience working on other projects, is that so how do you do unit tests? So typically, as a data engineer, as an engineer, your code shouldn't cross the boundaries of your IDE before you actually perform unit tests. So how do you actually do unit tests? Because Databricks only understands what the data source is in data lake, for example, and then how do you actually unit test it right from here? So which is where you have things like you will actually create. What we did in the project was we used PySpark to write the code locally in the Jupyter notebooks, and then using the Jupyter integration with Databricks, there's something called, I forget the exact name, it's been 2 years since we did that. It's actually called Jupyter Notebook and Databricks Connect, if I'm not mistaken, with which you're able to, right from here, you actually write the code, initially unit test with your local data set, and then you say, now I want to run this in the Databricks. So automatically through this connection that is established, the same code that you're running on your VS Code, for example, it gets pushed to the Databricks, which is a cluster which is running in Azure. Okay, and then it does the whole thing. So this is the whole notion of inner loop, which means that I'm not even checked in my code yet. Okay, so I'm just writing my code for the first time, and I'm using this particular integration to push my code into Databricks right from within VS Code here. It does that particular job. It is able to pick up data from a data lake, and then it's able to run the code, and then everything's fine. Now I know that the code that I wrote locally using PySpark and using my local data set works fine. So now you actually you check in that particular code, and then it goes through the motion of peer reviews, and it goes through the higher levels as well. So that's the whole thing about inner loop development. But what that means is that you also need to have the IT team coming into picture, because you need to have a particular port open on a Databricks cluster, because we thought that you won't be able to establish this connection. Okay, so some kind of admin work needs to be done before the connection is seamlessly established. But I strongly recommend that probably one of the teams should definitely go ahead and explore and use that to make sure that you are using the best tools and procedures to make sure you are actually building the software the right way. Okay. Yeah, the next point is that the Lakehouse architecture should also provide for a compute which caters to different workloads. We spoke about it. We have the Spark, and then we have the SQL analytics engine for the different kind of workloads. And then it should also provide for easy integration with the other tools and services. So which is where you see those on the right, where Power BI can just plug into the SQL analytics endpoint. And then right from within the Databricks Explorer, you can say, hey, no, let me sort of integrate with Power BI. You choose the partner connect feature in Databricks, and then you sort of hook onto your Power Bricks, sorry, I got both the names together, in Power BI, and then you'll be able to see the data from the Lakehouse, and then you can bring those visualizations on the fly without you having to do any kind of hard work on that. There are a couple of other tools mentioned there. One is the Azure Machine Learning Studio, which I said is our first party solution for building machine learning models, and the other one is Synapse on the top. And the one on the left below is actually called Data Explorer. But I think on second thoughts, I'll not talk about it. It's off topic, so I don't think it's really relevant. I'll just let that be. Okay. Okay, again, so this actually gives you a view of how so when you do your hack, I'm sure you'll have something of this architecture in mind, because you need to pull data from somewhere. You need to ingest the data, and then let it go through the different stages. So in this, while we are on this, I just want to mention that to import the data, so how do you actually pull the data? So there are various ways in which you can do it. couple of years back, we introduced this notion of autoloader in Databricks, which means that so when you actually have a blob store where data gets dumped on a regular basis, so how do you do a CDC or a change data capture kind of a thing? You don't want to do a regenerative thing where you pull all the data every time and then you decide in memory, hey, what is the news? What are the new rows in the data which I need to consume? So it's quite painful. But with autoloader, what it helps you do is that it already has something called structured streaming. So if you have a Kafka endpoint or it had a Azure Event Hub, it can connect to it directly. Databricks can connect to it, and then you can actually take the structure stream and then sort of act upon it. But if you have blobs getting dumped into a particular folder, and how do you sort of mimic that into something like a structured stream, okay, which is where autoloader helps you. It's almost like a publish, subscribe, trigger kind of a thing, event-based architecture where as soon as the file gets triggered, the Databricks notebook, you can configure how frequently it polls or sort of picks up that information. So it reads all that information and then gives it to you in the form of a stream. It's almost like you're getting a real-time stream from data that is put into in a batch mode into a blob store or a data lake store, and then it gives a feel of actually working with a streaming data source. It also has this notion of checkpointing, which means that if you actually stop this and then restart it, it should not obviously take back the same information. So it has those checkpoints where it's maintained state in terms of what was the files that were completely processed, and then it sort of totally glosses over them when it picks up the next set of files. Okay, so all those things are handled for you. So that's probably the most optimal way in which you can actually pick up the data from the blob or data lake source. Or you can use ADF copy. So Databricks, you can actually have ADF copy action as well, and then numerous ways in which you can actually go ahead and do that. Or you can also use data factory. But I know you're actually doing it on AWS, so you don't have access to that feature. So I suppose you should be using any of these capabilities to pull data from the different source system and then dump them into the data lake. Okay, I'm trying to see if there's anything that I need to emphasize upon, but I think we pretty much covered all the points here. I think we spoke of the SQL analytics already. So it has a SQL editor where you can, the analyst could run those ANSI SQL queries. Okay, you have a query catalog, you have dashboards and alerts. So Databricks also, SQL Analytics has a dashboard of itself where you can create different views and based on different queries and then based on aggregations, and then you can actually have those dashboards visible. But of course, they are inside SQL Analytics. But in case you wanted to publish it to users who are actually the senior leadership in the company, you can't ask them to go to a SQL Analytics endpoint. So which is where your Tableau and Power BI kind of tools help you. So that could be the one place where they all go to. So whatever is built, all the data that is analyzed upon here can actually reflect in Power BI. But for a person who is a data engineer or a data scientist, probably they want to see when they're building things and they can't wait for data to surface in Power BI dashboard. So obviously they need some kind of an analytics engine even as they're actually working upon it. So which is where these dashboards are extremely useful for them. Okay, so I think we pretty much covered all these aspects. Yeah, coming to the Synapse Analytics workspace, I told you that Databricks and Synapse Analytics gives you analogous means with which you are able to perform similar actions, how to build a Lakehouse architecture, the entire 9 yards that I actually spoke to you about. But an additional thing which I think is very important is that we have this notion of an industry model, which means that he mentioned the case of healthcare. So when you want to perform full-fledged analytics and actually derive machine learning, build machine learning experiments to create capabilities of forecast, so you need to have some kind of a data schema which is tried and trusted for that particular domain, and which you know that once you use that, you have pretty much all the use cases covered. It's very difficult for every organization to figure that out by themselves. So which is why actually Microsoft acquired a company called ADRM some time back, and ADRM has been in this business for several decades. So they have built tried and trusted domain data models and schemas which address all the pain points and all the requirements that each of these domains require. And those are actually distilled into an offering in Synapse Analytics. So we just go to Synapse Analytics and then go to the knowledge center, say, hey, let me sort of deploy this particular data model for healthcare, for example. It may not exactly be all that you mentioned, but I need to still look at it in the light of what I understood from you today. But it has a model for healthcare as well, and it creates an entire database structure complete with all those relationships. So what this means is that, so we have created already the structure. So all that remains is that, hey, now that I've got the structure for this particular domain, I need to pull the data from different source systems. Then you'll go to Synapse pipelines and create those pipelines and put the data into Delta table. And then, so you have data in Delta table, and then you have the schema based on industry model, which is in Synapse. You are just ready to good to go, okay? And then a lot of pain and sort of thing taken away from you. The best part also is that in case there are some nuances which are typical to your industry, you can tweak that model. So you can actually make changes to it, and then you can actually use that the way you think it is appropriate. Okay, so that's what I wanted to convey there, which is not covered in the previous slides. Again, as I said, this is one-stop shop where you can do so many things. For example, you can have data integration through the Synapse pipelines. You have management and monitoring using the Microsoft Purview. Okay, and then you can actually integrate with DevOps right from within Synapse Analytics, like you do with Databricks. We can hook up with GitHub, or you can hook up with Azure DevOps, for example, and then you can actually have all those pipelines managed as code and version control through all the CI/CD processes that you typically associate these activities with. Okay. As far as the database templates go, at this time I think there are 40 different domains for which we have those models with so many entities, and I'm sure the list will just grow as and when more customers actually come on board on that particular thing. Okay, so I think that's just a quick summary of what Synapse Analytics provides as a no-code database design. Like I told you that you create a Delta table and then use its feature to sort of introspect that particular Delta table. It creates a table structure automatically by itself. And then, or you can actually supply a domain data model. You can do it both ways. Okay, so you can actually choose whatever is appropriate. It simplifies data loading. So you just use Synapse pipelines to talk to a host of different data sources, and then you're able to build all those ELT and ETL pipelines for yourself and go through the Medallion architecture that I described already. The industry, the databases from the industry standard I just spoke to you about. So 40 plus are covered already in that. You can actually choose one of those for the line of business that you deal with. Query your data along the way, so you can choose whether you want to use Spark or SQL depending on the roles or the personas of who would be using those features. They have the tools that they are that they expect, and they are extremely comfortable working on those. You can sort of have business analysts hook on to all this data using Power BI through the seamless integration that it offers, and then they can actually light up all the different scenarios. And then you also have easy ML deployment pluggable. So you can just plug in your different machine learning pipelines into the data in the Delta Lake, and then you're good to go. And just one word of caution here. I just mentioned about the industry data models. It's not actually the BI model. Okay, it's actually like the OLTP data. It's the third normal form data model that you typically have. So that's what is represented here. So you actually choose those templates from the gallery. You create a schema and then show the schema in the Lake database, and then you run your pipelines and pull the data and dump them into the Delta Lake based on the schema that I've exposed. Once you do that, it's not yet ready for heavy aggregations. Probably you still need those star schemas because let's say you have slowly changing dimensions, for example. Okay, so you can't just say that a particular category or a type of a particular attribute changes with time. And then you have historical data as well. So you can't just say that I supplant that original record with a new value, and then so all the analytics will show you that right from day one the attribute had the entity had an X attribute, whereas till yesterday it was something else. I don't know whether I conveyed it effectively, but essentially, if you know what slowly changing dimensions are, that's what I'm talking about. So you need to be able to handle all that. So you need to have a star schema kind of a thing where while you have all the data finally represented in Delta table, you may need to handle some specific scenarios like SCDs that are slowly changing dimensions, and then create a star schema so that you are able to have a data model or a data mart which is geared to a particular scenario. Yeah, I think that's about. Yeah, I think that's pretty much sort of concludes what I wanted to share. Of course, I wanted to just demo the whole thing. Unfortunately, I couldn't do that. If someone wants to come to my laptop, probably I can show it to you. But I know you have a busy day ahead, and thanks for this opportunity. Any questions so far? Feel free to ask me anything that you.
Synapse, what is the security model working for? Especially data information, because emails, the provisos are that varies for example other tools. Do we have any integrated security model for this?
Yeah, so all the data movement in Synapse Analytics happens through the Synapse pipeline. So when you create a Synapse pipeline, you need to specify what is the source and target source system. It asks for credentials with each attribute. that you make sure that all and sundry don't connect.
It's not following kind of encryption kind of.
Encryption at rest is by default. So all the data is encrypted at rest. You can choose whether you want to have Azure managed keys, which is the default, or you can say, I as a customer want to embed my own keys because I don't want Microsoft to take a look and decrypt and look at the database or something. You can choose that also. So security is at every level. So I didn't emphasize so much upon it.
But actually, if you are following encrypted model, affect the performance.
No, it doesn't have impact. It's all fine-tuned to handle those kind of hygiene kind of requirements. Yeah, no, there will be no hit on the performance. And then we have this tool that I described, which is Microsoft Purview, which helps you classify information. For example, he gave the example of the healthcare industry where some data is very sensitive. You don't want to just share it all and sundry. It will classify those things automatically. Okay, it knows all those industry models. Looking at a particular table in the speech, it prompts you saying that, hey, I think this seems to be, it will flag all those, and then you can actually override and qualify it and do all of that. So whenever, and it also does things like the entire pipeline as it goes through getting transformed. So it probably started with 3 tables, and then it had 3 tables in Silver Store, and then you actually end up with 10 because you want to create a gold data store with different views of the same data. So at every stage, you know that that particular attribute in that particular data, which source system came from, the entire lineage tracking, all those things are available. So all those capabilities exist. Yeah, I think from security perspective, I mean, no stone unturned there. So. Okay, thank you everyone.
Thank you so much, sir, for the enlightening presentation. And we could understand a lot more about the data lake patterns in Microsoft Azure as well. So I would like to request Nitin Mallya, our Chief Technology Advisor of Nest Digital, to give or offer a token of appreciation to Srikanth and Shankaran. So please.
Thank you so much. Thank you.
So next, I think we need some refreshments, right? So we have arranged tea and snacks in the beside room of this auditorium. So we can take a 10 minutes break for all the participants and the speakers. Let's have, and we can come back after 10 minutes. we are moving to our next session. The next session was a presentation which is taken by the Nest Data Competency Team. So I would like to welcome Alan, Jisha, Anu, Arun and LB onto the stage for sharing your presentation.
Warm good afternoon to all of you. Myself, Alan. I will be just giving you a brief introduction regarding the one of the file formats that is being used in the big data system. So, as of all you know that nowadays we are dealing with numerous amount of data, and that also the data will be in large volume. So, how the data will be processed nowadays, we need to take care of that. What are the techniques used in how the data to be processed? There are various techniques used by the Hadoop system. So in Hadoop system, there will be some sort of technique. One technique which is used in Hadoop for dealing with the big data is the Spark system. So in Spark, basically it is a system which is used to process the data for big data workloads. So however the data is huge, we need this technique to process, to take this, how to provide some, detect the various patterns and how the data can be provided as a real-time insight, so that the data can be provided, the genuine data can be provided at the real time. So using this technique, we also have to use the various memory caching techniques so that the query execution will be fast, so as to provide a better performance and so as to for the given data size. So in Spark, it supports various formats, where there are various formats that it supports. So coming to the three formats which supports that, is the structured one, then it is the unstructured, then the semi-structured format that's the Spark supports. So in structured, there are Parquet file formats, Ivro, then ORC. Coming to the unstructured, there are TXT file formats and the CSV file formats. And in semi-structured, we have the XML as well as the JSON type formats. So while picking up any of the format and the data type, we need to find that what kind of data, there will be some factors through which we will be identifying the format of the data types. So some of the requirements that the file required is that whenever we get a data, whenever we are storing a data, it should get the reading of the data should be fast, or we should write the data to a file. It should be fast. It should be splittable. That is, multi-transaction can be, or the multi-execution can be done on different types of files. Also, if we have the data, it supports the schema evolution. That is, while storing the data itself, if we know that what kind of data will be stored in that, it will be a plus point for that file. So coming to that, we know that all type of files will not support all these features. We need to compromise on some of the factors based on this factors which is being displayed. So coming to when we talk about data, what we think of that, the logical storage that is being stored. we think that the data will be stored in a row format, whereas in each record will be containing different columns, and for another row will be, so it will be a column and row format. But actually in the disk, the data will not be stored in this format. In the disk, it will be stored either it has only two formats, which will be basically, it will be a row-based or the column-based format. So Parquet is one of the formats which will be using this kind of formats. So in a row-oriented format, the data will be stored sequentially based on each record. That is, each record with each column will be stored sequentially. Then coming on to the next record, then and so on, the third record. It will be stored as a row in the row-oriented format. Whereas in column-oriented format, it will be stored where all the columns will be stored sequentially. Then coming to the next column, or the first record will be stored, and so on. So this is the way which we find the data will be stored on the disk actually. So coming to the Parquet. So Parquet is used basically, it's a French word. Basically the meaning in English is wooden floor. So it was invented by the Hadoop system creator itself, Duff Cutting, in 2013. So basically post 2013, it has evolved so much that this is one of the file formats which is extensively used for data analytics purpose, because as the name suggests, it is the format is basically drives upon the column-oriented format, because comparatively to the row-oriented format, the column-oriented format is much faster and it is highly efficient, a data type format where we are not required to find any type of rows, and actually also we require that the data when we require some data, the data should not be where we do not require all the rows extensively. Only we are analyzing based on some fewer columns. So in that case, we need to orient the data in a columnar format. So that's why the Parquet is used extensively for this type of data analytics purpose. So what we find the characteristics of Parquet. So the characteristics of Parquet includes that the main characteristics is that it is based on column-based format, wherein which we are not required all the columns to be retrieved. Only few columns we need to be required for data analytics. So that is the second point. So it is used extensively for analytics purpose, OLAP use cases. And the third point is that it is self-describing. Self-describing means that as the data is stored in the metadata, so in the metadata itself, as it will be storing the type of data that will be storing in each column, and what kind of values will be present in that column that will be present while storing the data itself. So that's why it is self-describing. And moreover that it is a highly efficient type of format, because in this type of formats, we are basically dealing with the data. We are not storing the data actually in, we are storing the data in columnar format, but the data is not stored as it is. In Parquet, we are using the data, it will be converted, the data will be converted into metadata and all that. So in that metadata, we will be describing the data in the binary form. We will be converting the data to a binary format. And the last characteristics of Parquet, it will be following the word paradigm. Word paradigm means it will be writing to a file once, but we can retrieve the data later on as many times as it is required. So it is the fastest read process compared to other file formats. So why Parquet? So Parquet is basically used, as we discussed, that it is basically used for data analytics purpose, but the main feature of the Parquet is that it uses compression. So as we told in the previous slide, that it stores data in a binary format that makes itself that the compression can be used to a large extent. And there are various compression used in Parquet. That is some of the compression techniques used are run length encoding. In run length encoding, we'll be finding that if there are many repeatable values that is being stored in the data, we will not be storing the data repeatedly. Instead, we will be using storing the value once, and we will be storing the number of times that value is being repeated. So with two value, we can store the n number of values n number of times. Second will be the dictionary encoding with bit packing. In dictionary encoding, it is basically used where we are storing a large amount of string, where we require the high capacity of data string value to be stored. So likewise, for example, the string which is specified here, South Georgia and the South Sandwich Islands. It is a large string, so instead of storing the string as it is, we will be storing a integer value for each of these strings, and we will be providing this data as a mapping value in a table. So based on using this compression, we can increase the performance of the data. So the performance can be is high in Parquet file. Similarly, the schema evolution. So as described by Srikandan sir earlier, so in that the schema evolution, that when in the requirement, if initially we require only some columns to be derived, so in that case, when we are describing the column, we require only 2 columns to be required. In the initial case, later on we require that more columns to be done. So in that case, we can use the schema evolution. That is, we can increase the number of columns as and when required. Also, that, based on the schema evolution, we can split the values in this Parquet. So initially, a Parquet file will be containing a single column. Later on, it will be containing 5 columns, 10 columns. So that is why it is splittable. So we can split the Parquet files in different formats. Also, it is language agnostic. So it means that it's not dependent on a particular platform of language. So it can be written Parquet. Later on, it can be used in any of the applications using this Parquet file. Also, it supports complex data types. So this is somewhat the Parquet files looks like. So basically, it will be containing a file metadata. So in that, we will be containing the row groups, and within a row group, there will be a chunks of columns present in that. And in the columns, we will be having the page header. So within a page header, there will be many pages, and the data will be stored within that. So basically, a Parquet file looks like that in this format, wherein it will be consisting the root. So the root will be the directory where all the Parquet files will be stored. So in that, in each of the Parquet files, it will be containing the row groups, and within a row groups, there will be multiple columns, and in that columns, there will be the data page. So the figure below shows that it will be containing the raw data will be stored at the base. That is, there will be the raw data. In that, the columns will be present, and above that column, it will be within a row group, and the row group will be contained in the Parquet files. So this Parquet files has one of the main features called the predicate or the filter pushdown. So basically, this and also it uses the projection pushdown. Basically, the predicate pushdown of filter pushdown is basically used by all the DBMS, wherein we are filtering the required rows based on the requirement. And in projection push down, as the figure shows that it filters the data based on the column oriented format. So in projection push down, so the Parquet uses basically both the features, that is the predicate push down as well as the projection push down, that is shown in the hybrid based layout. That is the third layout, which uses both the row oriented as well as the column oriented push down in that. So if you try an example of a simple example that wherein we are storing a data, we have various integer values. So if we need to take the values which is less than 5, so in that case we will find out that it is stored in different row groups. So the first row group will be containing the value from 1 to 3, the second row group will be containing 4 and 5, and the third row group will be containing 6 and 7. So basically it will be storing the values. First row group will be containing the 1 and 3, so it will be included in that. The second row group contains the 4 and 5, so it will also be included. The third row group can be skipped. So before filtering itself based on the row group, we can filter out the records, so the Parquet is of highly efficient. So summarizing these Parquet features, we can find that it uses less space utilization. When we need to look up the data, random lookup, basically the filtering part, all that, it will be initially stored within a row group, so that the data can be retrieved much faster compared to other file formats. Basically, also it stores the basic statistics, that the aggregation features like the grouping, min, max, that all stored within the row groups. So basically, this is one of the main criteria of the Parquet files. Also, while trying to get the distinct values, the retrieval will be much faster in Parquet files. So comparing to other file formats, when we can find that it is a columnar based format. As it is the data stored in binary format, it will be highly compressible, and it is splittable because multiple Parquet files can be used for different purposes. Also, it can be support complex data structure as well as the schema evolution is supported in Parquet file. One of the drawbacks is that it is not human readable because the data is stored in a binary format, so we need to use various tools to convert these files to a readable format. And also, one more drawback of the Parquet is that it is while writing to a file, it is much poorer compared to other formats, that is CSV, JSON, Avro, and all that. But once it is written, the data retrieval will be the faster. So that's why the Parquet is one of the most popular tool used for data analytics in the basic the cloud engines like the data lake and all that. Parquet is used extensively. That's
Good afternoon, everyone. My name is Jisha. I'm from Nest Data Competency Team. Today my agenda is to speak about Spark SQL, Spark data frames and Spark dataset. All of you know what is big data and why big data processing is very important nowadays. Today we have a lot of big data processing tools available, and most popular open source big data processing tools available are Hadoop and Spark. Even though both Hadoop and Spark processing data processing applications over large-scale data analytics applications over clustered computers, each of them have its own features. Spark is 100 times faster than Hadoop, and Spark can process real-time data and as well as live stream data analysis can be possible with Spark. And let's look what are the components of Apache Spark. Apache Spark has 5 major components that are Spark Core, Spark Streaming, Spark SQL, MLlib and graphics. Spark Core is the main and major component of Apache Spark, and which is the basis of the whole project. All the other components are built on top of it. And Spark Streaming is it is the module responsible for real-time data processing. The processed data can be pushed out to file systems, live dashboards, and other databases. And Spark SQL is the module which is responsible for structured and semi-structured data processing. Next is MLlib. It's a machine learning library which includes a lot of machine learning algorithms and utilities such as regression, clustering, and classification algorithms. Next is graphics. It's an API used for graph-related tasks. Next, come to Spark SQL. As I said, Spark SQL is the module which is responsible for structured and semi-structured data processing, and it integrates the relational data processing capability with the functional programming capability of Spark. And it supports the programming languages Python, Java, Scala and R. Then it provides a programming abstraction known as data frame. It is a data structure actually, and it combines the data organization, and also it supports distributed query engine that can run queries in different nodes of a cluster. Then next is the languages used in Spark are high query language and normal SQL. Next is what is the need of Spark SQL. Actually, Spark SQL has developed to overcome the limitations of Apache Hive run over Apache Spark. In Apache Hive, actually the SQL developers write queries to queries in SQL way, and which is converted to MapReduce jobs. That is slower in nature. And the next limitation is Apache Hive cannot resume the job resume capability. That is, when if process fails in between, it cannot resume the job from the breakpoint. And next is Apache Spark SQL architecture. The bottom layer, that is the data store. That is different formats of data that can be CSV, JSON, JDBC, Parquet file, etc. The data from these data sources are fetched by data source API and then transferred to data frame API. Data frame converts or organizes this data into tabular form, and the upper layer, that is query processor, processes this data, that is data frame DSL. Next is data frames. Data frame is actually a data structure which integrates the programming capability and easy to use API, that is known as data frame API, which organizes the data into tabular form or like spreadsheet or data frames in Python pandas. And the only difference is that a spreadsheet, while a spreadsheet sits in a single computer in a particular location, the data frame can be span over thousands of computers. And data frame supports programming capability with the programming languages like Java, Python, Scala, and R, and it supports the data formats like Avro, CSV, Cassandra, etc., and the storage system supported by data frames are HDFS, Hive tables, and other databases. Next is Spark dataset. Spark dataset is also another data structure. It is the successor of data frame API, and it combines all the features of data frames and RDD. RDD is actually the predecessor of data frames, and it has all the features of data frames and RDD and avoids the limitations of data frames and RDD. It is strongly typed, that is, it supports compile time, type safety. It is released in the version Spark 1.6. Next is the features of dataset. As I said, dataset supports the compile time type safety, which means the errors can be detected during compile time itself. But in data frame, this capability was not there, so the errors could be detected during runtime only, and easy to use. It has a rich set of high-level functions provided, and it is very simple to use. Next, fast and optimized. It provides a catalyst optimizer. It provides query optimization very fast. Next, it provides a single API for Java and Scala. Next is conclusion. Actually, RDD, data frame, and dataset, all are the data structures provided by Spark SQL. All have their own APIs, and which provides data optimization and the data classification, etc. Then RDD was the oldest one and most basic one, and it does not have a schema for data. And next came data frame in Spark 1.3, and its successor is dataset, came in Spark 1.6. Only some few features are described here. Data formats supported by data frame are semi-structured and structured data. Dataset provides structured and unstructured data. And compile time type safety is not supported in data frame. That is, errors can be detected during runtime only. In dataset, compile time type safety is supported, so we can detect the errors during compile time. And the programming languages supported in Java data frame are Java, Scala, Python, and R. The object-oriented programming languages, Java and Scala, are supported in dataset. Actually, from version 2.0, the data set came as the default standard, as it has some more features, and it is widely accepted. Thank you.
A warm good afternoon. Today I'm planning to give a brief introduction about RDD, DAG, and caching in Apache Spark. As we all know, Apache Spark is a big data processing framework which gives a very fast access in cluster computing. and the core behind this this property is RDD. Let's go to the application of Spark. When we are this Spark we are using in multiple applications in real-time processing system like search engines and fraud detection engines. Let's take an example of Amazon recommendation engine. In an Amazon recommendation engine, we are giving we are searching for a product of our choice, and once we give our particular our specifications to the engine, the Amazon search engine will understand our requirements and it will give us back the product based on our specification. And all this is possible with Apache Spark, and the heart behind this process is RDD. That is, and in the current world is expanding in terms of technology, and the AI is the phase of this evolution. Okay. In ML algorithms, the data related to the data that we need to train multiple computers are very huge and are complicated. In map reducing technology, we are using traditionally we were using map reducing technologies to gather all these informations, and to get all these informations using these map reducing technologies is impractical nowadays because of the amount of data that we are dealing with. So we are using Apache Spark instead of these map reducing technologies in ML algorithms. And here for its processing speed, we are using RDD. The processing speed we are getting is only because of the help of RDDs. RDD is a distributed collection of memory where data needed is always stored and kept in RAM. This makes the entire process speed unbelievable, and it is fault tolerant as well. Now let's see what is RDD. RDD is the main logic unit of in Spark. It is a distributed collection of objects stored in memory or in disk of different machines of a cluster, which is used to process based on our requirement. And in RDD, it is read-only in nature. We cannot make any changes in an RDD, but we can create a new RDD from the existing one using the transformations on the existing RDD. An RDD in the Spark can be cached and use it again for the future use. This gives a huge benefit to the user. RDDs are said to be lazily evaluated because it will delay the evaluation until it's really needed, and this saves a lot of time and effort. When we are going for the benefits of RDD, it is time efficient, cost efficient, and less time in execution. After RDD, we are going to directed acyclic graphic DAG, and which will come after the RDD processing, and the DAG it will look like a flow chart, and based on the transformations or the commands given by the RDD, a graph-like structure will be created, which is more easy to understand. And in this, the workflow would be when we are giving an input to the DAG system, it will go to the DAG scheduler, and that divides it into multiple stages. From the task scheduler, it will go to the task scheduler, and the task scheduler, with the help of cluster manager, it will divide this smaller chunk of data or input into the executors. The executors can be n number, and the executors are acting as a slave here. So we can say it is a master-slave architecture. When we are going to caching, the transformation it it is a transformation in Spark. None of the transformations are saved until the subsequent action is performed. Using cache, Spark will always store transformation in memory. Thank you. That's it.
Good afternoon, everyone. Myself, Arun. I'm also from data time. And my topic is Apache Avro. Before we start with Avro, we have to know what is data serialization. Actually, data serialization is the technique of converting our data data into a binary or textual format. Actually, is useful for transferring the data over a network or to store it in a persistent storage space. So when we complete the transfer, we need transfer or receive the data from a storage space, we need to deserialize the data. So actually this diagram shows the data serialization process completely. And when we move to the main topic, Avro, actually Apache Avro is a data serialization system which helps to transfer the data between programming languages and the processing frameworks. And it is helpful for defining our data into a binary format, as well as we can map it into the programming languages that we use. When we come to the Avro structure, actually it is a schema-based system. So, and in the Avro read-write operation, a language-independent schema always associated with it. Actually, when we serialize the data, that has a built-in schema. Actually, in the serialization, it is used to serialize the data into a compact binary format. That is, we can deserialize by the data using any other applications. One of the advantage of Avro is actually Avro uses JSON format for declaring the data structure, and so it is easy in implementing any programming languages that is already using any JSON libraries. So these are the structure of an Avro file, and then we move to the framework of an Avro. Actually, Avro creates a self-declaring file format called Avro data file. In this file, it stores both of the data along with that data schema. So one of the advantage of that framework is the user does not need to compress that file. So actually the framework with the Avro makes a size optimization on all these files. So that is very useful in RPC, that is remote procedure call. And the client and server during that RPC, during the RPC, it transfer the schema during the connection handshake. So it is very basically useful for communicating the schema and old and new. So if there are any change in that field name or a new field name is added onto the new schema, it's very useful. Actually, this is the basic details of an Avro file. So, and comes to the next slide here. It is the data types that supported by the Avro files. Actually, it supports both the primitive and complex data types. Actually, primitive data types like Boolean, int, long, and string, etc. And the complex data types like arrays, enum, fixed maps, and Actually, this is the file structure of an Avro file. So here, it's an Avro file is a collection of headers and n number of blocks. Here, the header is consist of these three parts, such as a title that is that is a 4-digit ASCII character, and F followed by the file metadata, that is the schema in that JSON format, and along with that a compression codec is also attached with that. And next is the sync maker, that is useful for splitting and file for map reduce. And in terms of blocks, it contains the details of objects, that is number of objects in that particular block, and the size of that serialized object. Next, and followed by the actual serialized data, and other sync maker that is used to communicate with that header file. Okay. This is the structure of an Avro file. So when we go to the next slide, here it is an example of a JSON schema for a student record. Here the type is to declare the actual file type. Actually, record is the common type we are using, and the namespace is used to declare the space where the file resides, and the name is the schema name. We can identify a particular Avro file from a directory using that namespace and the name by adding a dot file. That is, here we can uniquely identify that particular file with the name dataflare.student. It is a unique name for a particular file. In field part, it is in field parts here we can declare the fields in a fields and its data types in that particular record. So this is the example of a JSON schema. When we come to the working of Avro, actually the working, we can describe this working of an Avro in these 4 steps, main steps. Actually, the first step is to create. We have to create a schema for our data. Then we have to read that schema file. We can choose 2 types, 2 methods for reading that particular schema. One is to generating a class file. We can generate that class file using an Avro. We can generate a class file of that schema using Avro, and the next step, next way is to directly passing library. We can use a pass library. We can directly read that schema using this parser library. Then the serialization and the deserialization. We can use serialization API and the deserialization API respectively for serializing and the deserializing of data. Then the advantages. Actually, Avro encodes the data in binary format, so its size is too small, and the schema is not sent with the data. So the data is smaller. So we can the data is smaller in size. File size is small. It supports schema evaluation. That is, if any change in the schema, we do not need to break all the functionalities. We can handle it in a less functionality change. That is an advantage of Apache Avro, and it supports the languages like C#, Java, C++, etc. Actually, then it is an Apache creates in a binary for structured format, which is compact, which is compressible and easily splittable. So these are the advantages. And when it comes to the disadvantage part, in C# Avro, it needs a .NET 4.5 framework for its best use, and it is potentially slower in serialization, and above all that, we need a schema. A schema is mandatory in Avro. That is, so for reading and writing data, schema is mandatory. So that is a disadvantage of Avro. So that's all from my side. Thank you.
Good afternoon, everybody. My name is Selvi Joy. Here I am presenting the topic on Spark Shuffle. And everybody know that the RDD is the basic and fundamental data structure that we used in the Spark. And it's contained a huge amount of the data, and it is divided into different partitions, right? But in some cases, in order to fulfill our some requirement, we need to repartition or the redistributing this partitioned data, and that is called shuffling. So Spark Shuffle is the mechanism of redistributing or repartitioning the data so that the data is grouped differentially across the partitions. And based on your data size, you may need to reduce or increase the number of the partitions of the RDD using the Spark Shuffle. So you just keep in mind that Spark Shuffle is a redistributing or reorganizing or repartitioning of the partitioned data. Okay, then let's move to an example. Consider a file. It contains the details like month, customer ID, item, and the price. First, we create a RDD from this file. So we create an RDD. It contains the 3 partitions. In the first partition, it contains the details of the October, and in second partition, it contains the details of November, and in the third partition, it contains the details of the December. Okay, my requirement or our requirement, our goal is that we want to calculate how much money and how many items and how much money was spent by the each customer over this year. In order to find our result, we want to use the group by key and the reduce by key in the Spark. Both group by key and reduce by key operations are called a shuffle operation because it triggers a shuffle, and it is also called a white transformation. So the operations that trigger a shuffle in Spark is called a white transformation. Let's check how group by key is working. Here, in the first stage is my original RDD, and it contains the 3 partitions. In the second stage is my mapping stage. That means I fetch my required field only. From my original RDD, I need only the customer ID and the money and the price of the items. So in the second stage, I'm mapping that details. So my second stage contains only the customer ID and the price. Then next, we want to group these details based on the customer ID in such a way that the first partition contains the details of the customer ID with 1, and the second partition contains the details of the customer with customer ID 2, and third partition contains the details of the customer with the customer ID 3. So in the from the second stage, it contains the details of the customer ID with the customer have 2 entries, so we can easily move that data into here. But the remaining 1 details is reside on the second partition. So we want to move that data from second partition to this first partition. And also consider the second customer. Here its details reside 1 detail on the first partition and 1 detail on the third partition. So we want to move that 2 details. So that is from 1 partition and the third partition, we want to move to the second partition. So in such a way that here happening a data movement from one node to another node through the network, and that is called what? Shuffle. So shuffle is the movement of the data from one node to another node through the network. And it's also is a costly operation because involve the data movement, right? So it has some performance impact. So in order to improve this performance, we use the another operation that is called reduce by key. And in the reduce by key, as the word suggests, reduce, we reduce the data on the mapper side, then move the data. So consider this example, the same example. The initial stage is our original RDD with the 3 partitions. And in second stage, that is the mapping stage. In that stage, we reduce the data on the mapper side. That is, so consider the customer details with the customer ID 1. It has two entries, right? So when we reduce the data, consider the customer with the customer ID 1, and it purchased 2 items. So the number of the item purchased to 2, and the total amount. So 3,000 plus 4,000, it becomes 7,000. So here we reduce the data from 2 entries to 1 entry. Then we move the data like group by key. And that is the shuffle operation that happened here. So benefits of this approach, by reducing the data set first, the amount of the data sent over the network during the shuffle is greatly reduced. So it can improve the performance of the shuffle operation. And that's all about the topic shuffle operation. Okay, thank you.
So firstly, I would like to thank each and every speaker who has taken a series of presentation over here. So I would like to mention this is our data competency team of Nest Digital, and I can see a remarkable effort behind these presentation, and thank you so much team. This one is something very momentous for Nest Digital. So now we are moving to our next, a small break session actually. We are conducting other talk shows and hackathon after our lunch. So nearly we are taking 45 minutes, and the lunch is arranged in the Rajagiri canteen. We will guide you to reach over there. Anything else? Let's move for a break, right? Yes. No, it's in another building. Yes. So let's go there.